topic for today's discussion is equilibrium of a rigid body. So hereafter mostly our focus is going to be on rigid bodies, and we had seen that the forces acting on rigid bodies can be divided into two groups. One, external forces. This we generally called it as force, EXT, or internal forces. This we have been denoting it as force internal. We had seen that these internal forces usually do not contribute. Either they do not contribute either for rotation, either for translation, or rotation. This we had seen. So unless otherwise we specify, most of the forces what we are going to consider are external forces. So we will simply denote it by F vector. And now remember, we have had so far, we have dP by dt, rate of change of momentum, is equal to force, and we also have and the rate of change of angular momentum is what we call it as torque, which is responsible for the rotational motion of the object. So whenever a body is subjected to force, then there is going to be a momentum or acceleration. Translational motion is possible, and due to torque you will have the rotational motion. Now we have the concept of under what conditions the system is in mechanical equilibrium. There are different kinds, a body may be under different kinds of equilibria. There is something else called thermodynamic equilibrium, chemical equilibrium. Right now we are concerned about the concept of mechanical equilibrium. So what is this concept? This is like this. If linear momentum is a constant of motion, this is that linear momentum is a constant of motion. That means linear momentum is conserved, it is not changing. Then in that case what happens? On the other hand, if the angular momentum is a constant of motion, I'll ditto here, it's a constant of motion, then what can we have? And so what happens in this case? This implies the sum of all the forces acting on the body. There may be several forces. Force is a vector, so sigma over I1 is equal to n, say. This becomes 0. So for mechanical equilibrium, system of all forces acting on the body must be equal to 0. This is what you call it as the translational equilibrium. So this is what you call it as, this terminology, translational equilibrium. Okay. Then next is if tau is 0. Maybe I'll write it here. If L is a constant of motion, then this implies, so various torques acting on the system, depending on how many of them, this is equal to 0. This is what you call it as rotational equilibrium. Okay. So what is the meaning of the first equation? The meaning of first equation is, I will write it here. Meaning of first equation is, remember it's a vector equation, therefore the sum of all the x component of all the forces is equal to 0. So if Fi is the ith force, the x component, and I am summing over all the forces, this is equal to 0. Similarly, all the y components is equal to 0, and all the z components is equal to 0. Now what this means is that torque is a vector. Again, sum of all the x components of the torques over all the torques acting is 0, and sum of all the y components of torques is equal to 0, and sum of all the z components of torques. And here I am writing in component notation these two equations. These two equations are in component notation, therefore there is no need to write vectors. We shouldn't write. Suppose we have coplanar forces, essentially a special situation, coplanar, for case of coplanar forces. And let us say that the system is under equilibrium. It is essentially like a two-dimensional problem, essentially a 2D problem. Two-dimensional means all the forces are acting on, let us say, XY plane. And then what happens? For the translational equilibrium, Fi is equal to 0. This means two conditions. What is it? Essentially, what is it? Sum of the x components is equal to 0, and sum of y components of the forces is equal to 0. So this is essentially two conditions. And you need to look for a direction which is perpendicular to this 2D plane. There is no rotational motion about an axis, therefore tau, there is going to be only tau about an axis. Tau about an axis perpendicular to F1 F1 and F2 vanishes. So essentially it is only three conditions, essentially. Okay, right. Now we will now let us say that we consider an important case. Suppose some of all the torques are acting on this body, they vanish. Now you may say that I am going to calculate these torques with respect to some other origin. Is it possible that the body will have rotational motion? The answer is no. The reason is, we will see that how. I will consider I have sum of tau I is equal to 0. This is for, I will call it as rotational equilibria Rg. Right? Is it going to remain valid? Does it remain valid? Does it remain valid? Does it remain valid if if the origin is changed? If the origin is changed. You will see that. It is very easy, simple calculation. I have the origin here, and one of the forces, this is the A, B, the 2 points here. Remember, it is it's a couple acting, minus F, and on this it will be F, Remember, these two have to be parallel. I mean, these two lines, but in opposite directions. This is B. I will join this. This is position vector R1. This OA vector is got position vector R1. Similarly, OB vector, the position vector is R2. So these two forces F and minus F constitute a couple on a rigid body. So now let us calculate the moment of the couple. Moment of the couple. This couple is, what is the moment of the couple? This is R1 crossed with the force, crossed with minus F1, then plus this R2 crossed with F. Actually it is here the force is minus F, therefore I should not write this one here, simply write minus F, then F, right? This is nothing but, this is what will happen here. This is equal to, what is this quantity? This is going to be R2 minus R1 crossed with F. What is R2 minus R1 from this triangle OAB? It will be AB. This is equal to AB cross F. So this simple calculation shows that when you calculate the moment of a couple, that is going to be independent of the origin. Whatever origin you choose, again it is the moment of the couple is AB cross F. Okay. So we can say that this translational equilibrium is independent of the location of the origin. And so rotational equilibrium, RE, remember what it is independent of the location of the origin. So if a body is under rotational equilibrium with respect to a particular coordinate system, and then what you do, you change the origin and look at it, still it will remain the same. That is the message. And okay. Now we will consider various cases as possible. The first case is like this. You can treat it as a kind of illustration, or I will treat it as an illustration. That means explaining the basic concepts. I consider a rod AB. This is A, B here, and you have the center here at C. This is little a, this is little a, the distance. This is a uniform rod of uniform cross section. Now you will say that there is a F acting, and then there is a F acting here. So this particular rod is subjected to two forces, F here, F here. Is there any? Now it will induce a torque like this. This force will induce a torque in this direction. This is going to be anti-clockwise, this is the clockwise. Both of them they cancel. Therefore tau is equal to 0. But tau is equal to 0 means it is under rotational equilibrium. Sorry. So it is under rotational equilibrium. And what about sigma of forces? Total forces is equal to F total. Sorry. Is equal to F total it is not equal to 0. In fact, that is equal to 2F. So obviously what will happen? This is a case where Is it under rotational equilibrium? Yes. What about translational equilibrium? No. It is not under translational equilibrium. Now we will consider the other case. This other case is like this. We will consider the same rod, and there is at this end I have a force acting like this. There is another force acting like this. It's a couple, strictly speaking. That's the definition. I have the center here. Now, only thing I changed, reverse the direction of one of the forces. In this case, what will happen? Sigma Fi is equal to F total is equal to 0. They are in opposite direction, therefore it vanishes. However, the sum of torques is equal to torque total. What is the total torque acting on it? So this will, with respect to this will have a torque in this direction. It is in the anti-clockwise direction. It is anti-clockwise direction. It is 2 times the torque due to each force. So this is not equal to 0. Therefore, what about translational equilibrium of the system? It is under translational equilibrium. Whereas, what about the rotational equilibrium of the system? No. This will rotate. So such a situation is what is known as such a situation where the body does not have translational motion, where it is under translational equilibrium. However, it rotates about a particular point and axis. This is what is called as a pure rotation. Okay. We will one special case we will see. This is what is called as a lever problem, common lever which we use. This is what is called principle of moments. Actually, this is taught even at a even at an early stage in a school. However, we shall discuss this from the point of view of translational equilibrium and rotational equilibrium. So I have a simple lever like this. What you have is you have a fulcrum. This is what you call it as a pivot or fulcrum as it is known, and this is subjected to, here there is a force. This distance is d1 and then this distance is d2. Call this point as A, call this point as B. Okay. Right. Now this pivot point you can call it as O, about this particular point. Now what happens? Now this body, this whole rod will have a ideally speaking, a lever should not have any mass, so it's of negligible mass. So an ideal lever has negligible mass. So there is going to be the two forces are one force is acting here, another force F2. It will have a moment like this. It will induce a moment. This will induce a moment like this. Finally, it will be there. So generally, what you do is, this is the load arm. This section is known as load arm. This portion is known as load arm. This A to O is known as load arm. Then O to B is known as this is effort arm. See, what you do is there is a weight here which requires to be lifted or moved. you have here effort on some force you are going to apply. Okay. Now there is a forces are acting here, therefore there will be a reaction at this particular point. Reaction at the fulcrum. Reaction of the support at the fulcrum. This is a vector quantity. So the reaction at the fulcrum, at the support. Reaction of the support at the fulcrum. Okay. So for translational equilibrium, for translational equilibrium, what we need, this R must be equal to F1 plus F2. Now, taking moments, now there are three forces acting essentially, F1, F2 and then the reaction. It's also of a force variety. Now, taking moments about this particular point 4, moments about O. What do you get? Here this moment is, moment due to F1 is F1 into D. F1 into D1. And this is, because this is a translational equilibrium, now you will see that this is must be equal to F2 into D2. So this is for rotational equilibrium, you have this condition. For translational equilibrium, you have this condition. And so from this you can, so this object is not rotating at all. It is in equilibrium. It is neither rotating like this nor it is rotating like this. Both these moments are cancelling with each other. So from this we have F1 by F2 is equal to D2 by D1. And so this is what is known as mechanical advantage. See, what we want is ideally, if F1 is much larger than F2, let us say, then in order to maintain this equilibrium, we need to have this distance D2 much larger. That is the idea. So D1 is much smaller, and this is a common sense experience. And okay, for battery input waste. Now we will go into concept of center of gravity. எவ்வளோ டைம் ஆச்சு?
35 minutes.
35. Okay. Center of gravity. வர்றப்போ சொல்லுங்க. The concept of center of gravity. It is a common experience that you would have seen. Everybody can do it. If you have a notebook or a cardboard, it can be held on at a particular point. At a particular point O, one can vertically hold it so that this book or cardboard, it is balanced. Okay. So how does this happen? So there is going to be reaction at the tip. This reaction at the tip, what we call it as R. This reaction at the tip is going to balance the total weight of the book, mg, of the material, of the book or material of the book, let us say. So the notebook is under translational equilibrium. It is under translational equilibrium, and not only that, it's also under rotational equilibrium. Why? Otherwise, if there is the different forces acting here, they can tilt like this or tilt like this. It's not happening. So not due to it is not due to unbalanced torque. If there is going to be one, it will tilt. So what happens is the center of gravity. This is, now we define what is known as the center of gravity. CG. The center of gravity is located such that the total torque on the body, center of gravity so located such that the total torque on the body due to the forces, let us say that there is a M1G, there is something else M2G, etc. So the total torque due to different forces, they balance, they cancel out, and so torque is equal to summation over I Ri. So this is the R1 vector, okay, that crossed with whatever is the mass at this particular point and acceleration due to gravity, that is equal to 0. So what happens is the center of gravity of a body is that point where the total gravitational torque on the body is 0. So this is this definition of center of gravity. The total gravitational torque acting on the body must be equal to 0, and so Ri and G are perpendicular to each other. Therefore essentially you are left with Mi Ri summation is equal to 0. Okay. At this stage one would think that this is same as the center of mass, but is not. Remember, the center of mass definition is this quantity divided by the total mass. And however, it will turn out to be the same if the origin is the center of mass of the body, right? If origin is going to be the center of mass of the body, then it will turn out to be the same. So what happens is that the center of mass and center of gravity, both of them will turn out to be the same if the body is subjected in a uniform gravitational field. So center of mass is equal to center of gravity in a uniform gravitational field. What time is it? 29. About 35 சொன்ன மாதிரி
இல்ல சார் என் ஃபோன்ல தான் டைம்.
ஐயோ
ஸ்டாப் கிளாக்.
இதான் கரெக்ட். Right. Now if G on the other hand, if G varies from point to point, if the G is going to varies from point to point, then center of mass and center of gravity do not coincide. Now how is center of gravity of a body determined? And it's again a very standard one. Suppose I have a cardboard or something and I want to find the center of gravity. So this is a very standard procedure. What you do is you suspend it from a particular point A. Suspend it from a particular point A. This point is A. So the whole the weight is going to act along this, so it will be along this direction. Now you take some other point B and suspend it again. Then its weight will act along this. When you put it this way, when you fix this whole body about fix it about the point B. So similarly, you will find that various lines will intersect. Suppose I have another point C here and do this. So this is the center of gravity. So this O is the CG of the body. Okay. We will work out an illustration. We will work out a simple problem and it will illustration. You can treat it as an example. Various concepts which are involved. We will put that. So I have a rod. This end I will call it as A. This end I will call it as B. So there is a pivot here, K1. There is a pivot here, K2. it's obvious that there will be a reaction here. This is R1, this is R2, R2. So this will I have the CG of the body. Why it is coming?
This is normal plate, sir. Pen
Okay. So this is G. The weight will act down. Right? Let us say that this weight is weight. Remember, mass times weight is what? Mass times acceleration due to gravity. This is 4. Then I have another weight at this particular point P. Let us say that this is the point P. There is a weight W1. This is W1 is given to be 6 times G. Okay. Now K1 and K2 are pivots or knife edges, whichever way you want to take. There are few dimensions given in the problem. I will specify that. AB is 70 centimeters, namely the length of the rod. Then AG is because this is the center of gravity, 35 centimeters, right? And AP is given to be 30 centimeters. So obviously PG would be 5 centimeters. Okay. Then we need certain distances. What is this AK1? AK1 is equal to, and AK1 is equal to BK2. This is the location of knife edges. It's 10 centimeters. And, so we know what is K1G and K2G. K1G is equal to K2G is equal to, so 35 minus 10 is 25 centimeters. Right. Now we have it is under translational equilibrium. Therefore the forces acting upwards, R1 and R2, must be equal to forces acting downwards. So translational equilibrium implies R1 plus R2 to reactions must be equal to W1 plus W. So we can have this. So R1 plus R2 is equal to W1 is 6, W is 4, therefore 10G. Okay. This is one equation. Then I will label it as 1. Now taking moments about G for rotational equilibrium. Right. Now it is going to be in the clockwise, whereas this will be in the anti-clockwise, and W1 with respect, we are taking moments with respect to the point G. So this will rotate in this direction. So minus R1 into, what is the distance? K1G, plus R2 into K2G. This plus, there is one W1 acting here, W1 into PG. sum of all the moments is equal to 0. So we can substitute the numbers. This is 0.25 in meters. K2G is 0.25 meters. P1G is just 5 centimeters here. P1G is 5 centimeters, therefore is 0.05 meters. From this you will get an equation. R1 minus R2 is equal to 1.2 G. Strictly speaking, I should put, if I want to write the units, I should write newtons here. And some little bit of arithmetic is involved, do it. Now from these two equations, you can calculate R1 and R2. R1 is equal to, if you add these two equations, 2R1 you will get, from the 2R1 is equal to 11.2, then R1 would be 54.88 newtons and R2 is equal to 43.12 newtons. And, right? So it is very easy to do these kind of problems. All that you need to do is so all that you need to do these kind of problems is to write the balancing equations for forces and write the balancing equation for torques, namely translational equilibrium condition and rotational equilibrium condition. When you take when you write down the rotational equilibrium condition, you need to take torques about a suitable point where your algebra would be simpler. And now we will consider an illustration, another problem. But there are different kinds of problems that are involved which are repeatedly asked in examination. Various things can be asked. One is a ladder problem. And, this I will call it as an illustration or a problem. You can treat it as a problem or example. This is what ladder problem. Ladder right now. So the situation is like this. I have a wall. I have a ladder here. This is a ladder. Ladder is AB. The wall is smooth. The wall is smooth, whereas the floor is rough. I can have this also rough, this also smooth. We will do this. So this point I will call it as D. This is C. Call this point as C. So the weight will act downwards, M into G. And now, what are the various forces acting? That's what first we should sketch very clearly, indicate very clearly, then indicate the directions of torques also very clearly. Now, because the wall is smooth, there is going to be a reaction here. This I will call it as N2. I need to have a little longer one for reasons you will realize why. This is N2. Then, because it is rough here, what happens is, you have here a frictional force F, and this is what is going to be the normal reaction of the floor on the foot of the ladder. Now, these two forces can be combined into one. I mean, I'm not indicating it very clearly. So, this is going to be the F. This particular one is what is going to be the F. Sorry, I need to do it. This is F. Now, when for equilibrium, when I produce this, when this force is produced, they must meet at a particular point, not a bad diagram, and this point I will call it as O. Why should they meet there? In that case, what happens? If they don't meet, what will happen? Because if they meet, what will happen is all the torques about this particular point will be zero. Therefore, it will be under really rotational equilibrium, and it's also under, we will see this. Okay, AB, length of AB is L, right? And we will call this angle as theta. Which angle? The angle made by the ladder with the floor as theta, right? So what is F, sir? Actually, F is nothing but the reaction of the floor, on the foot of the ladder. Okay, now let us work out. It is under translational equilibrium and also under rotational equilibrium. So translational equilibrium implies sigma of all the forces is equal to 0. What are the forces acting, sir? We will have it as we can have there are two kinds of forces, one along horizontal direction, one along vertical direction. Therefore, we will have it as two equations, and sum of all Fy is equal to 0. F of x is equal to 0 implies is equal to there are only two forces, the forces along the horizontal direction. N2 is one force, it is acting at A. There is another force, namely the frictional force F, which is acting at B. Therefore, F is equal to N2. What about the forces acting along Y direction? Only two. One is the weight of the ladder, which is acting at the center of gravity, and the reaction at this particular point. This implies N1 is equal to mg. Two important equations we have got. All that we have done is to make use of translational equilibrium, nothing more. Now, rotational equilibrium. So, sum of all the torques, this must be equal to 0. About which point I would like to calculate? And I would like to calculate net torques about B. And so I will say that net torques about the point B. You can choose any point you want. Earlier we already seen it. Then what will happen? Then this will rotate in this, the weight of the body will rotate in this direction, in the clockwise direction, whereas this N2 will rotate it in the counterclockwise, anti-clockwise direction. So mg into the foot of the perpendicular from this particular point, that will be equal to what? This length will be L by 2. This whole length is L by 2. This is L by 2 into cos theta minus N2 into what did I do? I should drop the perpendicular to this. That would be whole thing into sin theta. This length into sin theta. L sin theta is equal to 0. So I will have N2 is equal, I will cancel this. N2 is equal to, I know it is already equal to F. Here that will be equal to mg into cot theta by 2. Now I know what is N1, I know what is N2, therefore I can calculate what is the total force. F is same as N2, therefore total force. What is the total force? Actually it is the reaction of the floor on the foot of the ladder. This will be equal to square root of as from this particular figure, I have here N1 squared plus F squared. This is same as square root of N1 squared plus N2 squared. This is equal to N1 squared is mg squared 1 plus cot square theta by 4. So this is nothing but mg into square root of 4 plus cot square theta divided by 2. This is the magnitude of the force. You can also do a little bit of calculation to what is the direction of the force. The direction of the force is given by what? Suppose this is going to meet at this particular point, I need to give some name. So the direction of the force, the direction of the reaction, direction of the reaction of the floor, reaction R is given by this angle OBE. That can also be calculated from little bit of geometry. And now we will consider one more example. Now this again one of the typical problems is ladder problem. Another typical problem is what we call it as you keep a heavy block on an inclined plane. This kind of problems are called as inclined plane. We will call inclined plane and I would call it as block or blocks placed on inclined plane. This is another typical problem. I'm not going to write down the problem, but I will describe the physics of it. Physics of it is like this. I have an inclined plane, this is theta, and I have a block which is placed on it. H is the height of the block and so-called length of the block or a side of a block is B. Okay, the weight will act from the through the center of gravity. This will be mg. This is maybe I'll reduce it a little bit. And this can be resolved along two directions. This is mg cos theta, and this will be mg sin theta. This is mg into sin theta. Okay. One need now when let us say that suppose this particular inclined plane, we can rotate about this void, let me say. Then this plane, this particular top portion will coincide like this. Then the block is placed on this. Now I can rotate it, let us say that. I can rotate the inclined plane. That means the angle theta can be increased. When the block is on the floor, mg will act downwards. The reaction will also act, the normal reaction will be here. Okay. Now if I keep rotating, what will happen? at there is a situation when this block can topple. When the block will topple, this normal reaction will no longer act through the center of the CG. So normal reaction will be in some other point. This is going to be the direction of normal. So as you keep rotating, when you reach a particular point, let us say, as you keep rotating, this n will move. So this distance we will call it as, this distance is what, x. I will produce it so that you will know clearly. This distance I will call it as x. So the point of application of n will shift from this line towards this, and the body will topple when n exactly coincides with this particular side. And okay, now this kind of problems can be done. This I will call it as A. This point I will call it as A. This point I will call it as B. That's all I would need. Now I will write down the block has two tendencies. One, the block can slide down. It is the translational motion. The block can slide down. So one can write down for translational equilibrium. For translational equilibrium, sigma of F must be equal to 0. Then rotational equilibrium, we don't want this to topple. Therefore, sigma of all torques, I can take it about a particular point. I am going to take it about C. This must be equal to C. I am going to take torques about this. Now, what about the translational equilibrium? What does it mean? It means first, horizontal forces. What are the various horizontal forces? Horizontal in the sense horizontal to the side of this block. Here there is a frictional force F. Therefore this F must be equal to this. This is the only force that is acting along this direction. Along this direction it's the mg sin theta. Therefore F is equal to mg sin theta. Then n is equal to, this n is equal to mg cos theta. Now, what about the torques about the C? It will be equal to this will have a torque about this point C, that is this implies n into x. This must be equal to and F, it is also going to create a torque F into perpendicular distance from here h by 2. So from these three equations we can discuss when the toppling will take place, whether the toppling can take place before sliding, or sliding can take place without toppling, etc. So various such situations we will discuss in the problem session. Thank you.